This presentation is about modelling rail brake in continuously welded rails. On some projects in the USA, there is a requirement to check for rail brake under large thermal differential temperatures. In other words, the size of brake in the rail has to be assessed to ensure it is under the limit allowed. There are several ways of doing this, but codes do suggest that a refined analysis is required in which the superstructure, substructure, continuously welded rail and rail fasteners are included in a single model. And this can be done in LUSAS in a 3D model. Rail alignment can be straight or curved and can also include turnout and crossovers if required. The example we're going to look at is a straight 2-span continuous bridge with spans of 120 foot each, with 4 72-inch deep bulb T girders and an in situ slab, with the decks restrained longitudinally at the pier and free at abutments. With 2 tracks, therefore the model has 4 rails. Here is the model in LUSAS, where you can see the rails and precast girders and deck slab. As you can see, the rails and girders are modelled with beam elements with eccentricities. They're the pink elements in this model, and the deck slab with shells. That's the green part. In the example, we have rail fasteners longitudinally spaced at 30 inches, and they're considered rigid in the transverse and vertical directions on the bridge, and the rails are extended beyond the abutments 900 foot each side. We will look at temperature differential of 70 degrees Fahrenheit in the rail and 20 in the deck, down to minus 125 degrees in the rail and minus 55 in the deck. The structural forces induced by thermal loads include the fastener longitudinal slip force of 3.2 kips per rail fastener, a fastener longitudinal stiffness of 18 kips per inch per rail fastener, and with the rail gap control, the fastener longitudinal slip force of 2.2 kips per rail fastener for thermal analysis, and longitudinal stiffness of 12 kips per inch per rail fastener. The forces induced, as you can see in this model, can give stresses in the rail, forces in the deck and piers, and reactions in the bearings and so on. Here we can see the longitudinal forces induced in the rails. By introducing a brake in the rail, we can see that the gap that occurs under the extreme thermal cool condition, which in this case is 3.64 inches, and which is likely to be outside the project limits, so would have to be looked at in more detail. This ends this example.